So this is a presentation on the transformer, and the transformer is basically made up of three parts. You have your primary coil, you have your secondary coil, and you have your soft iron laminated, you can see it's made out of sheets here, laminated core. So how it works is you put an alternating potential difference across your primary coil. That produces an alternating current through your primary coil. And of course, when you put current through a coil of wire, you get a magnetic field around it. The strength of that magnetic field, the flux density, B, depends on the current. Depends on the number of turns in the coil as well, but it depends on the current. So as the current gets stronger, bigger, the field around the coil gets stronger. As the current gets weaker, as the current falls, the field strength falls. When the current then, because it's alternating, flows the other way through the coil, then the direction of the field reverses. So you have this alternating field, this changing magnetic field that's growing and getting weaker and then growing the other way. This field goes through the secondary coil. And you know, when you have a changing magnetic field around a conductor, you have an induced PD across the conductor. So the alternating PD over here induces an alternating PD over here. And if you have a complete circuit here, then you will induce an alternating current. So that's what's happening here. And these shifting circles are meant to represent that changing magnetic field. So the idea is that you can put whatever your supply PD is here, your primary PD here, and you can get a different secondary PD. And the ratio of the turns in the coils dictates the ratio of the PDs. So this is your formula, Vs over Vp equals Ns over Np. You could have it the other way up, Vp over Vs is Np over Ns, but that's your transformer formula. A step up transformer increases the secondary PD, makes the secondary PD bigger than the primary. So step up is a reference to increasing the PD from primary to secondary. Step down is decreasing from primary to secondary. So in stepping up, the secondary coil has more turns than the primary coil. And a step down has fewer turns in the secondary compared to the primary. Now, nothing is absolutely perfect, nothing is 100% efficient, and there are energy losses in a transformer, but the designs are such that the energy losses are really very small. So transformers are 99% efficient. So you could have energy losses due to the I squared R heating, the current of the primary and secondary coils. The current will cause heating, and that heat is lost energy. You could have energy lost due to changing the magnetic field around the core. When you put the core in here, it becomes magnetized as well because the direction of the magnetic field around the primary is changing. It's changing the magnetic field around the core, and so you're making the core change its magnetism. That takes energy. Now, we're making it out of soft iron, and the idea, what soft means is that it is easy to magnetize and demagnetize, so less energy is lost that way. But you also have a conductor, a piece of iron, in a magnetic field that is changing, and so you induce currents in the core. And those induced currents, called eddy currents, they will cause heating. So to reduce the current, you need to increase the resistance. And this is where the lamination comes in. Rather than having one solid lump of iron, which would have quite a low resistance relatively, you have sheets of iron, laminate sheets of iron, and they are separated by layers of insulator, glue, for example. So you have the same amount of iron, but the resistance of that iron is much, much bigger because it's got lots of insulator in between the sheets. And so the currents produced, the eddy currents produced, are much smaller, and so the heating is less. So the final thing to mention here is that normally in a real transformer you would wrap the secondary over the primary so that all of the field produced around the primary goes through the secondary. They're separated like this so that you can see the different components of the transformer, but in reality this coil will be wrapped over the top of that one so that all of the field due to the primary goes through the secondary and none of the field is lost, which would be an inefficiency. So the power of the transformer, the power that you put in by the conservation of energy, is a maximum of what can come out. So what can come out can be no more than what goes in if it is perfect. But of course it isn't perfect. So some energy will be lost and what the power out will be slightly less than the power in. However, the power is the PD times the current. So if I double the PD from here to here, so if Vs is twice as big as Vp, then Is must be half as big, so that V times I here equals V times I here. If I make that twice as big as that, then that has to be half the size of that, so that this times this equals this times this. So by stepping up the PD, we're stepping down the current, which is where step-up transformers come into the national grid, of course, because by stepping up the PD, you are stepping down the current, which means you reduce the heating of the cables, so you increase the efficiency. Here's an example calculation. You have 50 turns in the primary, 20 volts AC. And in the secondary, we've got 200 turns, and we can and 80 volts. And so we can calculate the current in the secondary. And you can see we've gone from 20 volts to 80 volts. And so we would expect the current to be a quarter of the primary current, which it is, because that is 4 times that is 4 times that. So therefore, that must be 4 times that. Another sample calculation, 20 volts, 100 turns, 3 amps, and then 25 turns, 5 volts. Well, given that the PD here is 4 times smaller, we'd expect the current to be 4 times bigger, and of course it is.